Oh, this is the first and this is the fourth part of the chapter 5.4, and we will talk about the using diagonal matrices to carry out a linear transformations. And as I mentioned as the first part of the chapter, our final goal is transform vector x into the new vector A times x when A is the matrix. And this kind of calculations can be computationally costly, so we would like to find some diagonalized matrix D which help us to carry out easier calculations to conduct the same linear transformation. And theorem 8 actually allowed us to do just that. It's tell us that if we have a matrix A which diagonalizable, that is, it can be represented as a product of some matrix P, which contains the basis of the transformation, times diagonals matrix D times inverse of matrix P, then we can just use our matrix D for the transformation. Especially if we have a basis for our N formed by the columns of our matrix P, then our diagonalized matrix D is the B matrix for our transformation. And I know it's a mouthful of stuff, so I'll like to write it down as a simplified process. So what we're doing here is just taking our vector x, and we will write it down using some basis of our N. In other words, we will multiply it by inverse of our matrix P. And what we get is our same vector x, but now written in the different basis. So then we can carry out multiplication or linear transformation by multiplying by the easier diagonalized matrix D. And what we will get is our image, AX, written in the basis B. And then, of course, we can go back to our original representation of our image by multiplying by the matrix P. Let's just go step by step through this process that it will look a little bit less mysterious. So let's say we have a linear transformation from R2 to R2, and it's represented carrying out by the multiplying by the matrix A here. Not really hard, but still a lot of computations. So let's find the basis for R2 such that the matrix T is a B matrix for the diagonal matrix. Basically, we're trying to find the diagonalizable transformation. And hopefully matrix P, which will consist from the eigenvectors and make our multiplication much easier. Okay, so let's just go through step by step. First, we need to find the eigenvalues. And again, we form the characteristic equation, determinant A minus lambda I is equal to 0. Then we solve it, reduce it to the quadratic polynomial, find the 0 of this polynomial using quadratic formula, and come up with the two eigenvector. The first one is equal 5, and the second one is equal 3. Okay, now we can go ahead and find the eigenvectors corresponding to these eigenvalues. Let's start with lambda is equal 5. We need to solve the homogeneous equations when our matrix A subtract by our eigenvector 5 multiplied by identity matrix. So we can write down the augmented matrix of the system, solve it, and find one of the eigenvectors. So I choose, because we have a free variables, I choose the one which is conveniently represent the vector is 1 minus 1. So when we repeat for lambda is equal 3, again forming the homogeneous system by subtracting 3 times I from our matrix, write down augmented matrix, solve the system, and choosing vector v2 is equal 1 minus 2. Okay, so we are actually ready to answer the main question of this problem. So we need to find a basis for B for R2 with the property that the B matrix of T is diagonalized matrix. Because we are find two eigenvectors corresponding to two eigenvalues, we can write a matrix P and the diagonalized matrix D. So we are ready to report the basis as just the two eigenvectors V1 and V2. But let's just go ahead and construct the matrix P by just putting this vector together in the matrix, and finally write down the diagonal matrix D by taking the diagonal matrix and putting our eigenvalues on the diagonal. The first diagonal element is 5, corresponding to the first eigenvalue. Second diagonal element is 3, corresponding to the second eigenvalue. So now, when we have this matrix D, we can choose absolutely any vector X, and instead of multiplied by this matrix, we can go through like indirect process, writing it down in the basis B, multiplying by the diagonalized matrix, and coming back to the original space by multiplied by a vector P. So basically, important thing to remember here, that our mapping from X to AX or from U to DU is the same linear transformation. It's just the bases are different. So but when we are using our matrix P, which consists of our eigenvectors, we can carry out this operation.